Hello everyone, and welcome to the channel. I am Flask, and we are going to start by solving integration using the trigonometric substitution. So please bear with me. So it's really important to know that there are three case scenarios that we need to take into consideration. It's important to know that you must use trigonometric substitution whenever you've got this type of binomial. For example, a squared minus x squared in the denominator. It's important to point that out. So if that's the case, that means that we write our a, whatever our a is. So basically we take the square root of our a squared, and then our x equals a sine of theta. And then, of course, we take the derivative of this, which is the x, of course, and then we put our a times cosine of theta. It's important to keep going until you get to d theta. This is conceptual stuff, but it's important to put that this is only one case scenario. There are other two, which I will write it down really quick. Yeah, so whenever we have this binomial, once again we take the square root of a, and then once again we put our equality, which this time will be equal to a tangent of theta. Perfect. So then once again we take the derivative of a. The derivative of tangent of theta is secant squared of theta. Once again, d theta. We need to be consistent. Okay, so this is our second case scenario. Now let's jump straight into the last case scenario that we may encounter. Yeah, so whenever we've got x squared minus a squared, once again, I am doing this, although it's obvious. It's better to put it than not putting it. So we take square root of a, but now the difference comes at the time of putting our x equals a. Now this time will be secant of theta. And then with another color here, now we take the derivative of this, which will be a. The derivative of secant of theta is, yep, you are right, secant of theta, tangent of theta. And although we don't have more space left over here, we will cramp it a little bit, d theta. Okay. Yeah, so now we've got these three possibilities. Okay, so this is like the nitty-gritty, to put it that way. Now we will start by solving a really straightforward problem. So we've got 1 over the square root of x squared minus 4. Now, you've got to be careful here. And don't forget, of course, the dx, because you are taking the integral of a derivative. You cannot do it any other way. Now, you got to evaluate the denominator. And yeah, since you've got this, you need to apply. Well, first of all, you take the square root of a, which in this case is, well, the a squared is 4, then a equals 2. And then you do the trig substitution, which is the most important part. So you put x equals a times secant of theta. Okay, of course we do the substitution right there, and instead of a, we put the number, which in this case is 2, and then we go ahead and take the derivative of this. So once again, the derivative of secant of theta is secant of theta tangent of theta d theta. Yeah, it looks like a lot, but it's not too bad. So I will jump straight into the next step. So the next step consists in plugging in, basically, and getting rid of certain things. So I will show you in the next step. All right. So now what we did here was, of course, just plugging in. So this is what this turns out to be. This is what ended up being. And then, yeah, so we've got our 2 secant of theta, tangent of theta, d theta, and then in the denominator, we've got this great chunk. So it's not a big deal at all. What we got to do, of course, it's squared, this whole thing. So I will write it down right here, which is 4 secant squared of theta minus 4. And then you may think, oh no, it's a square root. What am I gonna do? Well, it's not a big deal either, because you pull the 4 out of the equation, you are factoring it out, and then you've got minus 1. Yeah, I know that this looks alien, this looks strange, but it's not that bad actually. So since this is a product, we can take the 4 out of the square root, and because this was 4, this turns into 2, and then we've got this thing right here. Okay, so it's important to know certain properties, certain algebraic identities, like for example this one. So you got to memorize certain properties. So I will write it down in the next page. Yeah, so for example, we just ran into this case scenario. So you want to get to this because you cannot take a square root of a binomial. So uncomfortable. So you just change things. Sometimes it's the opposite. So that, for example, you get tangent square root of theta plus 1. And then if that's the case, of course, you need to change it into secant the square root of theta. But since we've got 2 and the secant the square root of theta minus 1, you put your tangent the square root of theta. So this is what we get. And then it's possible to take the square root of tangent the square root of theta. So we just rewrite it. So we've got tangent of theta, and this will cancel out with this whole chunk. So the tangent cancels with the tangent, The 2 cancels with it. Well, actually, these 2, yeah. I am just trying to avoid copying everything over and over, but it's not that this is multiplied to the other thing, just that we are canceling this out. And let me show you. We ended up with our secant of theta d theta. And what's the integral of this thing? Oh no, it looks weird. Again, it's not a big deal, but this is something that you got to know. You could use the reduction formulas. Of course, that might work, but there is a really straightforward way to put this. So you put ln, natural logarithm of secant of theta plus tangent of theta. And are we done with the problem? No, we're not. Why? Because we cannot leave this in terms of theta. We got to go to our x. So now this is a key part. So I am going to explain to you how the triangle works. So let's recall that our x equals 2 secant of theta. So this is really important because we are trying to get back to x. So this means that if we isolate secant of theta, we end up with secant of theta equals x over 2. Okay, x by 2. And you get to know trigonometry at an extent. Okay, so we know that secant of theta is the hypotenuse. This is our hypotenuse. We'll express it as h. And this is our adjacent. Okay, so I will put it as adjacent. So in order to get to our tangent, we know that that tangent is our opposite versus over adjacent. Okay, so we got to draw a triangle in order to understand better the problem. So we've got our angle here. Our hypotenuse is x. This is our adjacent. Our adjacent is right here, is 2. And then the opposite is unknown, okay? It's right there. Yeah. So then we need to use the Pythagorean Theorem. So x squared equals, and then we put the sides, we include the legs into the equation. So it's b squared plus 4, and then what we got to do is isolate our b squared. So we just do this, and then we are not looking for b squared, so we take the square root of both sides, so that we don't affect anything. Okay, so we rewrite it, and as we know, we go back, and it's x squared minus 4, and then we can go ahead and finish it off. So our secant, okay, so it's our secant of theta, it's our hypotenuse over adjacent. So it's x over 2. And then our tangent is opposite over adjacent. So since that's the case, our opposite is the square root of this chunk. And then our adjacent which is right there, is 2. And are we done? No, there is still a long way ahead. No, I'm kidding. The only thing that you need to do is to add a c, and we're done. So why a c? Well, that's what you get to add whenever you encounter an indefinite integral. Otherwise, if it's a definite integral, which we will do next time, of course you don't include c because you just use the fundamental theorem of calculus, which we will cover next time. So don't forget, if you've got an a, a b, and then you've got f of x dx, which this is a definite integral, you don't need to include your c in your final answer. So thank you so much for watching this video. I really hope that it was helpful to you, and I will see you soon.